Alright, so now it's time to start working physics problems. So the first one we'll look at is just a simple one-dimensional collision. So it's about the easiest thing you can have. So let's say we have some mass, we'll call it A, and it's moving to the right with some velocity VA. And then we have another particle B, and it's moving to the left with some unknown velocity. So it's VB, but we don't know what it is initially. Okay. And then let's say after, so we have our collision, and then after the collision, we're going to say that mass A is traveling to the left with the velocity VA prime. Mass B, we don't know what it's doing. Okay, so mass B, it could be stationary, it could be going to the right, it could be going to the left. We really don't know what B is doing. Okay, but we can deduce that by what happens to A. So let's say the question tells us, we know the magnitude of the velocity of mass A. Let's say we know mass A and we know mass B. Okay, so we'll say this is what's given to us. Okay, and we want to find the change in momentum for mass B. Okay, so how can we do this? Well, we know that so there's two ways that you can think about solving this. So let's look at the way I think a lot of you would approach it first. So the first thing we do is we say, well, we know there's conservation of momentum. So that tells us that MAVA plus MBVB is equal to MAVA final plus MBVB final. Okay? And so if we do this, you can try and solve for it, but let's because we're saying, this is our initial momentum, this is our final momentum, and there are going to be some problems you have where this is exactly the way to solve it. Okay, but this isn't one of them, and the way that you know it's not is because we have one unknown and a second unknown, so we have two unknowns. So with two unknowns, we know that we need two equations. Well, conservation of momentum only gives us one. So we need to try and think about something else to solve this. Okay, so the easier way to look at this is we know the change in momentum of the first particle is equal to the change in momentum of the second particle, but in the opposite direction, right? It's the negative of that. You'll remember this from the video because we said that if A is traveling to the right with some momentum, and then it has a collision and it's traveling to the left, there's this impulse, right? There's this change in momentum, and so that's telling you that it's giving some of its momentum to mass B, and the other way around. You can look at it as mass B is traveling to the left, and then it's giving some of its momentum to mass A, and then it goes in the other direction. So either way you want to look at it, they both have a change in momentum that's equal in magnitude and opposite in direction. So now all we need to do is find the change in momentum for mass A. Well, that's easy, right? Because the change in momentum is just mass A times VA prime, its final velocity, minus its initial. Remember, the final velocity is the one that's positive because this is its momentum now, and then we're subtracting what it was before, right? Well, these are just vectors. In this case, it's just a one-dimensional vector. So its final velocity is is, so okay, so we should have been given the final velocity as well, the magnitude of the final velocity. So we'll say that this is Vf and our initial velocity was just V. So we have our final velocity is minus Vf because it's going to the left. It has no y component, right? And then we subtract its initial velocity, which is just V, again, only an x component. So our change in momentum is just ma minus Vf minus V0. So our change in momentum for B is minus our change in momentum of A, which is equal to ma times Vf plus V. Okay, so we have our answer now, so let's see if it makes sense. So the first thing we check are the units. Well, momentum should have units of mass times units of velocity, and sure enough we see this has mass times velocity, so we're good. And then, so the second thing we want to check is, does it make sense? Okay. Well, what we see is that we had A coming in initially and bouncing back to the left. So if A's being pushed to the left, then it makes sense. We expect that the change in momentum of B should be to the right. And that's what we have, right? That's what our answer shows us. Now remember, this doesn't mean that B is moving to the right. For example, B could have had a much bigger momentum than A. So that's just saying that its momentum, it would lose some of its velocity going to the left because some of its momentum is being shifted to the right. But in this case, so our answer definitely makes sense. And so we know that this is the right answer. Okay? And this is about the easiest problem that you can get in this. So we'll look at a couple more that are starting to get a little bit more difficult.